Okay, let us start with some reminders and then see how it goes. So what we had last time, I mean, the central tool in the whole theory is the Ito formula. So let me just remind it to you. Okay, what was the setup? The setup was that we had several random processes, xt, and then it was like a single, I don't remember, say m, what was the number of variables, and then it was a single vector valued process formed of all them. And then the question was, okay, if I think about some function of these semi-martingales, all them are semi-martingales, what can I say about its increments? And the answer was that, similarly to the standard calculus, what you should, I mean, the increment is given by the sum of first derivatives, okay, of xtd xtj, right? But then it was another term, 1/2 sum of second derivatives xt, and here it was a bracket of two semi-martingales. Okay. And it was a differential notation, which is just a shorthand. You don't, yeah, it should be S, thanks, everywhere. And what you do, you basically, instead of writing the sign of integration, so you just say, okay, let me denote this equation by saying df is equal to sum of that, of this and some of those. Okay, good. And then it was a new paragraph called Levy's characterization of the Brownian motion. And actually, so I thought a bit, and I also would like to include a sort of another material into this paragraph, so I'm going to rename it. But it's okay, I mean, with the old name too, so, and the local time. So what was that? And here it's not necessary 1D, just Levy characterization of the Brownian motion. So what's the important new thing is this local time, which I'm going to discuss today. So, okay, what theorem says? Theorem says the following. So assume we have a martingale, which is again vector valued. This is now a local martingale. Such that if I square it, I mean each of the components, and subtract c, this is again a local martingale, and if I multiply 2 with different indices, this is also a local martingale. Remember, this is exactly to say that the quadratic variation of this is t, and the quadratic and the bracket of this 2 is 0. Okay? And what's important with continuous trajectories, as always. The claim is that in this case, xt is an n-dimensional Brownian motion. So the message is that actually we saw, for instance, for one-dimensional Brownian motion that there are many, many martingales, like bt squared minus t, bt cubed minus something, I don't remember what, 3btt or something like that, and so on and so forth. But you know, to prove that something is a Brownian motion, it's enough to know only first two. And the reason is again just in the fact that for continuous local martingales, it always exists the quadratic variation, so the deep reason. Okay, so before giving a proof, let me start with some proposition. So what's that about? It's just a computation, basically. Remember also we had this notation for the class of local martingales. So let M be a local martingale and take some complex number fixed. Then the process C, which I also maybe later will denote this way, though we have only 2 lectures, so it's not clear if I have enough time. So what's that? By definition, this is the exponential of mt minus lambda squared over 2 mnt. So I just introduce a new process. And the claim is that this is again a local martingale. And there is a name for this guy. It's called the exponential martingale of M. And simple remark is that we already saw this in the case of the Brownian motion. One-dimensional Brownian motion. So this is one-dimensional process. We already saw it. This is exponential of bt minus square root of t. And the proof, of course, cannot be anything but just a computation. So we have this tool, right? So we know how to proceed if there is a function of a semi-martingale. We know how to compute, it's again a semi-martingale, and we know how to compute its martingale part and its bounded variation part. Okay, so it's just trivial computation. Let us perform it nevertheless. So for just let us make it in a more general, in a slightly more general case. Okay, this is a function of M and its quadratic variation, right? So just some function of 2 variables, which is, of course, very smooth, C infinity. So just imagine that this is some function from C2, and let us compute df mt mmt. Okay, easy. This should follow from here, and indeed it does. So what's that? It's and I'm going to denote the variables x and v because okay, this is the variation. This is yv. Okay, so what's that? This is the partial derivative with respect to x by dmt plus the second partial derivative in x dmt plus another term here, partial derivative in v d and mt. Or maybe it should be here, I don't know. Is clear what happened? Maybe it should be here because this is still the first derivative. Okay. So the message is that, okay, so if f satisfies this partial differential equation, then fmt mmt is a local martingale. It's a good question it's a good point to ask questions if you have something, because this is, the very, very standard application of the eta formula, and so if you have some...
Are we not supposed to have also derivatives like xv?
Oh, like here, so that's a good question. The point is that if, so what is the bracket of two semi-martingales? By definition, it's just the bracket of their martingale parts, right? So if you just write the bracket of quadratic variation m, it's 0. And the reason is that it's smooth enough. If you just approximate, it tends to 0. So it was somewhere, it was one of the lemmas for the eta formula that actually doesn't infer the result here. Okay? So, okay, this is a local martingale, and then what I'm saying, okay, this particular function hopefully do satisfy this equation. Well, actually, I was slightly cheating in this proof. So what was the cheating? The cheating was that this is for real valued processes, right? And this guy, okay, it works if lambda is real, probably, and m is a real martingale, real valued martingale. But actually, what I'm going to do is to apply it for complex values. Okay, let us leave it as an exercise. Do you see the point? So formally, you should do computations with real parts and with imaginary parts separately. Okay, hopefully everything works as it should, and I'm not going to check it. Just an exercise. Fix details with complex numbers. If you know some detail on complex numbers to be fixed, like, I don't know, zeros of the Riemann zeta, please fix it in this exercise. Okay, so, well, there are several ways. The most straightforward is just to say, okay, here I have instead of exponential sine and cosine, and the product of sine and cosine, and do all the same computations. Or you can just generalize the eta formula right here to complex valued processes. Okay? So I'm not going to spend time on it. Anyway, this is very straightforward. Okay, good. And now, and it's also related to the remark I had for the Brownian motion. So that time I formulated it for real valued lambdas, but actually it works for complex. Okay, and now what is the proof of Levy's theorem? Characterization. So, well, we want to prove that some process is a Brownian motion. So basically, we want to prove that something is a Gaussian variable. Well, that all the increments are Gaussians. What is the simplest way to do? this just compute the characteristic function as usual. So that's, you know, over and over the same idea as in the central limit theorem. Okay, so let's do it. So let us introduce first. It was a vector valued process, and this is a total mess with the super index. I'm sorry for this. Okay, maybe this is capital N. I mean, it changes all the time. I mean, it's either capital N or small n, and either in parentheses or not. So, okay, that's some vector valued process. And let us fix just a concrete vector there and consider the scalar product. It's just scalar product in RD. So what I'm doing, basically, this is a reduction to the one-dimensional case. So this is one-dimensional. And again, this is a trivial computation that first, sure, this is a local martingale. And second, the quadratic variation is now what? These guys are orthogonal, so this is xi1 squared plus xi2 squared plus etc. So this is just a local martingale. So this is nothing but the reduction to one-dimensional case. Okay, and now what I'm saying, okay, then by proposition, I know that the exponential of what? Let me put here I of I. Do I need any lambda? Okay, maybe I even don't need any lambda. So let me put it this way. Nope, what I'm doing. Just that, and that's it with 1/2, right? I mean, what I'm doing, I just put lambda equals I inside. Okay, this is 1/2. So this is the exponential of plus what? Square root over 2t is a local martingale. But actually, there is no point to put local here. Why? Just because it's now bounded, right? So this is purely imaginary. So the exponential of that is modulus 1, and this does not depend on the probability space. Okay, so I can erase local here. Just because it's bounded. And then what I say. Okay, then it allows me to conclude that for any pair of times, the conditional expectation of that given Fs is, okay, maybe let me write it first in full. So Fs is the same at time s. And this is obviously the same as to say that the conditional expectation of yt minus ys given Fs is exponential of what? Of minus 2 t minus s. Okay? Hopefully it works. And basically that's it. So because first you see this does I mean this is independent of fs. I mean this is just some number, right? So it means that this variable is independent of fs. And is normally distributed. Basically, that's it. Because we know this for any xi, any fixed vector. So we know this is a Gaussian vector which is independent of the past and is distributed as a vector valued Gaussian. Okay? Easy. I mean, when we have this, that's it. Okay, good. And now let us discuss some example, and then okay, see how it goes. So, okay, let Bt be a one-dimensional Brownian motion, and let us denote a new process, define a new process. Bt, which is the stochastic integral of sine ds dbs. Here something should be said about the sign. I mean, what's the function? Right now it is not of big importance. Why? Okay, let me write what definition I'm going to use all the time. So the sign of 0 is going to be -1. Though in the exercises sheet it's still 0. Okay, but right now actually it's not of big importance what happens when bs is 0. Why? Just okay, note that. This vanishes. Why? Okay, we know that the expectation of this squared is the expectation of the indicator squared ds, which is 0, because the Brownian motion is, I mean, the 0 set of the Brownian motion is of Lebesgue measure 0. So here, this is basically the comment that it doesn't matter which definition of the sign of 0 I take. Okay? Here, okay, it works. Is clear? I mean, what happened? What happened there? Right. So then, simple claim is that beta t is again a Brownian motion. Bm, which is defined on the same filtration. So the computation is actually trivial because, well, we know that, okay, Bt is a local martingale. And we also know that the quadratic variation is nothing but the integral of this sine squared. And this is t. Okay? This is 1. if at this point, so let me let me comment on this discussion, which probably looked a bit ridiculous. I mean, it's more general processes, in particular, if I do not know anything. At this point, it might be better to be sure. But right now, okay, I know I know anyway for the Brownian motion. It doesn't matter. Okay, good. So quadratic variation is T, so we just apply Levy theorem. Okay, let me delete this part. And what I'm going to draw now on this left part of the blackboard is a discrete cartoon of what's going on the right. And the idea is just to have some intuition on what's going on. Okay, so I had some Brownian motion. I constructed something else by this formula. Then I claim again this is a Brownian motion on the same filtration. And actually you will see in the exercise sheet that it's actually defined on a strictly smaller filtration even. But okay, what does it mean? What this construction means? Okay, discrete cartoon. Okay. Imagine that we work with simple random walks. And I use the trick I already used in my lectures. So it's going to be a simple random walk on z plus 1/2. So bt, simple random walk on z plus 1/2, started 1/2 z. So here is a sample of the trajectory. No. Something like that. And then, what is bt? I just declare b beta n plus 1, say b sine bn, sorry, b beta n plus sine bn by the increment. So you can think about this like I construct this beta starting from this equation just for ordinary differential equation, just by iterations. Okay? What does it mean for, what does it mean here? It's bn, beta n, this is n. Let me try to do so up, down, still down, then I must reverse still down, this is here. And then again I must reverse like this. To make a picture clear, I need some strange color. Okay, maybe this one. So what's that? This is the absolute value of bn. So what you see is more or less the same. The claim is that bn is the absolute value of beta n is the absolute value of bn minus the number of intersections. Number of crosses. So remember, this is exactly the picture we had in exercises. Maybe with the opposite sign. It was there. And the claim is that, okay, if I start with such a simple random walk and make this transform, then again, what I have is a similar simple random walk. Okay? So, and this is a straightforward analogy of what's going on there. Okay? Great. And then let us discuss how one can define a similar process in continuum. So the question, how one can define similar to this process in continuum. Because remember, in that discussion, so I mentioned that, okay, we have a maximum process for the Brownian motion, and there is an analog of this guy, which is called the local time. And that's exactly what I'm going to define now. So, okay, need some space. Tricky, but I continue here. So yet another application of the eta formula. So here is the goal. So the goal is to define that. And we know that to define this this process, it seems to be enough to define beta. Right? So okay, beta is here. And the only question is, I can do this formula. I can just say, okay, let LT by definition be what it must be, be bt minus that integral. Right? So this is a natural definition. The only question is, okay, if I can make sense of some statements about this process, it must be increasing, right? Because here in discrete, it's just a counting process. It counts the number of intersections. I mean, if I can make this picture, in a sense, clearer. Okay, so let us make a simple computation. Let us fix some epsilon and take the function bt squared plus epsilon squared and apply the eta formula to here, to this function. Okay. What's that? Now it's a smooth function, so I just differentiate. This is the first derivative, and the second derivative hopefully is that, and maybe it should be 1/2. If it should be 1/2, nope, it should not. I think this is correct. Okay, so what does it say? Okay, you can just write if the Brownian motion was started from 0, so you just write that this is epsilon plus dbs bs squared plus epsilon squared plus this error term. So this is a local martingale. This is actually an increasing process. And well, now you have you have a straightforward idea. Just pass to the limit when epsilon tends to 0. So basically what you expect to appear is that here this is the absolute value of Bt, right? This disappears, of course. Here is some local martingale. And here, okay, some increasing process. Okay. So there is a discussion of that in exercises, I mean in the last exercises sheet. But basically, okay, there is some technicality just to prove, okay, there is a convergence and there is some limiting process. Denote LT note. And again, in exercises, it's rather easy to see, I mean, it's fairly easy to see that actually note is constant on any interval uv, provided Bt does not vanish on this interval. I mean, the analogy is here again. So, I mean, here, okay, it's clear, but here you can, I mean, in continuum, you can just deduce it from the definition. It's not hard. So, at the end of the day, so what we have, is an increasing process LT note, which is constant on any interval which is free of zeros of Bt. And also it satisfies some properties. Okay? So basically it's written here. I mean what the properties are. Okay, good. And then, so this is A. Then B. Again, this is an exercises that this is actually can be reconstructed from B, from the absolute value of Bt. There is something to prove here. This is not totally obvious. So this discussion already happened a month ago. It's not totally obvious, but you know, here there is a way to prove it. And in particular, it means that Bt again can be reconstructed from Bt.
Isn't it just variation of absolute value of Bt?
This? Nope, not at all, because, okay, that's the other way around. When Bt moves, no, this is just unrelated. When Bt moves, this is constant. So here, this process would be zero, zero, plus 1, plus 1, plus 1, zero, constant, etc. So this is real not, if you wish. No, this is not a variation. It's a sort of counting zeros of Bt. So that's something deeper. Okay, so well, you have like 4 items in exercises on all that. And let me now conclude the first half of today's lecture by several more remarks on this. well, just think again about this. I mean, the formula which is basically here. So let me rewrite it. In a sense, it was a definition of our LT node, but in fact, there is another way here in exercises to define it. Okay, just think about this formula. And well, it quite reminds the eta formula which I just erased, right? So this is f bt, where the function is just the absolute value. This is okay, just derivative. F prime ds, right? And here is now a term which replaces the second derivative. Over replacement of what? Of the term which was 1/2. The second derivative was, what is the second derivative? The second derivative is a delta function. That will not be s. Okay. Now it's well defined. And moreover, so just a claim without any proof. One can go, I mean, one can push this route further and define not only the local time at 0, but the local times at all the levels simultaneously. So let me say it in a more formal way. So the claim is that for any, basically for any continuous semi-martingale xt, there exists a family of processes LTA, increasing processes, processes indexed by real numbers, such that an analog of this formula, such that the following holds. Some notation I'm going to explain what this means, and here plus integral of over R what should I say? Sorry for this. I should write just the local time LTA, that's it, d okay, f prime dA. So this is some formula. This is must be thought about as a generalization of Ita's formula. So, and it holds for any convex function, basically, or difference of two convex functions. So if you have a convex function of f, or convex function of a single real variable, like an absolute value, or a sum of them, it's differentiable everywhere if you think about left derivatives or right derivatives. So this is the left derivative. And then the second derivative is a measure on R. So the claim is that you can always, for any semi-martingale, and there is 1/2, of course, lost. The claim is that for any continuous semi-martingale, you can do basically the same as we did for the Brownian motion at level 0. So there are increasing processes which are called local times, and you can write a generalization of the eta formula in this setup. And the very last remark is that be here. So it was say A and B. Is that basically the computation here proves another theorem by Levy, which I already mentioned. And it says that for one-dimensional Brownian motion, started from 0, the process is mt minus bt mt, and the process absolute value bt lt naught has the same distributions. How to see it? Just instead of thinking about the same Brownian motion, I mean, what we need is that two distributions are equal. Just think about beta instead of b in the left-hand side. So just think about distributed in the same way as what? Here I should put okay, let me check what exactly just supremum of minus beta minus plus beta beta t supremum. And what I claim is that this is exactly that. So why? Let us try to figure it out. What I'm saying is basically, yes, so what I'm saying is that, okay, if I prove that this is the same as LT naught, then I'm done. Because, right, I have this formula which relates BT and LT naught. I mean, if I prove that this is equal to that, then the first parts coincide automatically, because I know what is the absolute value of the Brownian motion. So this is BT minus LT naught. So this is the only part I need to check. And for this part, I know that, okay, LT naught, this is an increasing process. In particular, I know that this is a supreme over 0t Alice naught. And at each particular time s, I know, yeah, sorry for this mess with blackboards, maybe I can do it other way around, like this. And for each particular time s, I know that Ls cannot be, I mean, it's strictly, it's greater or equal that minus, so this is minus BT. That LS is at least minus BS, right? So this is at least, is at least, yes, minus BS. Just because the difference of 2 is something non-negative. And to prove the opposite, just say, okay. To prove the opposite, just say, okay, at a given time t, let me just consider the last time before this when BS was 0. Consider max s less than t such that BS was 0. And at this time s, this disappeared. So what we know is that Ls was equal to minus Bs. And after that time, we know that LT note did not change because it doesn't change on intervals free of zeros of Bs. Okay. Not extremely clear, just sort of an exercise to complete the picture. So what you should do is, I explained one inequality. The other inequality, just consider the last 0 before t and check it comes into equality. Then you know that 2 components coincide, and then you deduce that actually the first components coincide too. So from here you deduce that the first components are also equal. Okay, so the picture is that, I mean, in this strange color, maybe brown, I don't know. In this strange color, what's written is that we have BT and beta T defined on the same filtration. Moreover, this small guy is a function of the big guy. And these equalities are just pointwise. It just holds. And what the theorem by Levy says is that distributions are the same when you replace beta by another b. Of course, they're the same. Okay. Note that nevertheless, the filtration generated by beta is strictly less than the filtration generated by b, because this is a function of the absolute value of b. So this is something non-trivial happens. I mean, this is not as simple as in the discrete cartoon. Okay, that's it for the first half. Let us have 10 minutes break. Good. Let us continue, and this is the second half of the paragraph announced last time. So that's after re-enumeration, resplitting, this is called Dubin's-Schwarz. Theorem and conformal invariance of the two-dimensional Brownian motion. Okay, what was this about? Let this be a local martingale. And for simplicity, let us assume that the quadratic variation of this guy tends to infinity almost surely. So this is a random increasing process, so let us assume it tends to infinity. Actually, okay, let me comment on this in a minute. Actually, this is not of big importance. The claim is that then there exists a Brownian motion Bs, beta s, such that Mt is just beta m. So what is the meaning? The meaning is that local martingales, they're just randomly reparameterized Brownian motions. Okay? So there are two remarks. And the first remark is a stupid one, just a sort of a warning. The filtration Bs has nothing to do with the filtration Ft. So we had a process, it was defined on some filtration, and this Brownian motion, it lives somewhere, I mean, in the another space over here. Okay? And the second remark is that, in fact, this condition is not necessary. But then what happens? So if with positive probability this limit is finite, in a sense it means that here, I mean on the Brownian motion side, what you have is a Brownian motion only until up some stopping time. And then to make the claim correct, this is basically an issue of probability spaces. So in this theorem, this beta will be defined on the same probability space as M, equipped with another filtration, of course, but on the same probability space. Is not necessary, and if we would like, to have a full Brownian motion, the cost is enlarging the probability space. So here it's going to be the same. If we would like to have a full Brownian motion, okay, maybe this martingale was just trivial, right? It was just constant zero. Not a very interesting example, a bit boring. And the probability space was trivial, just with a trivial sigma algebra. And then I claim, okay, there is a Brownian motion. Of course, it cannot be defined on the same probability space. It must be enlarged. Okay, good. So proof. This is very straightforward, though there is one subtle point. We'll see it in a minute. So let us denote, this reparameterization. So I'm going to denote the stopping time. Okay. And with the indices, let it be tau s. Okay. Tau s plus be the infimum of all times with mm strictly greater than s. Okay. This is of some importance. Strictly greater instead of say greater or equal. Why? Because it might happen that our martingale MT is constant for some period. Okay, like in this boring example, this is just a constant. But it might happen, okay, this is a random process, and again, there is some random set of intervals where MT is constant. Okay? And then the claim is that, well, not the claim, just a remark, note that this mapping is right continuous. Maybe it's good to have a picture somewhere. Here is a sample of my process MT. So this is MT. Versus T. So here is a sample of quadratic variation. And on this picture, I already claim something. So quadratic variation is an increasing process. And what I claim is that, okay, it might happen that it's constant on some intervals. Essentially, it's going to be a lemma that these intervals are the same intervals as here. But right now, okay, this is S. And this is tau S plus. Yeah. Good. And then, what I'm saying is that similarly, let us define tau S minus, which is basically here. And again, this is left continuous. And then what I would like to say is, provided some lemma holds, so it's going to be in a minute, just denote let Bs be defined as M time tau S plus minus. I need some lemma here. I need to know that these two values are equal because they are defined through the quadratic variation. And what I'm claiming is that they are equal on the for M itself. Oops. Okay, you have an idea how it should be. Okay, so what is the lemma? The lemma is that almost surely the set of all intervals will be such that U is MT is V for any T in E is the set of the intervals such that the quadratic variation does not grow. Both are random sets of intervals. Okay? So assume we already have this lemma. Then what I would like to say is that basically there is nothing to do. So then we know from lemma, we know that Bs is continuous. Almost surely continuous. Right, because we know it's both left continuous and right continuous. We know also it is adapted to filtration f tau s plus. Remember that for each stop in time, and this is of course a stop in time, for each stop in time there is a sigma algebra of everything that happens before. So, okay, this is a filtration. And if you are careful with measure theoretical issues, this is actually a complete filtration because of right continuity, because of the definition of this tau plus. And well, moreover, you know that okay, this was a martingale, a local martingale. I mean, MT was a local martingale. And moreover, we know that, of course, the expectation of what? Of say B. Okay, what I'd like to say is that this is a true martingale. Why? Just because okay, it's trivial. Just because what can be the problem? The problem could be only if beta is very big. Is that beta and this quadratic variation is very big. So just say, all right, this is essentially how should I say it? Maybe I can say it this way, m tau s, and this is bounded. So I can apply optional stopping. So now we apply optional stopping to tau s tau r, for instance, with r less than s. And then what you see is, okay, the expectation of well, again, just some mess here. Let me repeat what I would like to say formally. So formally, I would like to say not this. Excuse me. I would like to say that not beta s, but m c mean tau s plus is a true martingale. And this is just by definition. Okay, there is no beta at the moment, so there is just m. And then to which I apply the optional stopping is this m. Okay? Plus is m tau m plus. And moreover, we know that not only this guy is a true martingale, but also its square minus this is a true martingale. Because this is again, if we know that the quadratic variation is bounded, then we know that we can, I mean, we know that this is a true martingale and this is a true martingale. And so we can apply optional stopping to the second two. And tau squared plus. And basically that's it. Why? Well, okay. This means that the expectation of beta S given for plus f tau plus is beta r. Oh la la, la 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 la, and nobody corrects me. And we are lost. Okay, here of course this is also incorrect. I mean, I don't know anything about the quadratic variation of this martingale. So let us do it slowly. Okay, it was a martingale. I introduced a change of time, right? Then I said, okay, I have a new process. This is a continuous process provided I have such a lemma and it is adapted. And then I say, okay, this is a true martingale. To write this, I should write quadratic variation here, not the time itself, right? I mean, this is a stupid statement. It cannot be true. I mean, it should be m squared minus its quadratic variation, right? And this is not the quadratic variation. Okay, so it must be quadratic variation there. It must be quadratic variation here. And then what I say, okay, this is trivial because just by our definition, it means that, okay, the expectation of beta S squared minus S is beta R squared minus 1. Okay, as often the difficulty is that there is absolutely nothing deep here. And because of that, it's very hard to, to proceed. It's too easy. Okay, maybe just in words. The message is that, okay, if you have a martingale and you reparameterize it by stopping times, you still have a martingale. This is what optional stopping says. And the same happens with quadratic variations. Okay, the only fact is that now instead of the quadratic variation, you have just S. This is the definition of our stopping times. Okay, so we are done modulo this lemma. And for the lemma, let me swap the boards. The proof of lemma. Again, there is nothing deep. So first, there's a set of intervals. What I'm saying is that due to continuity of processes, it is enough to check the statement for a fixed interval. It is enough to prove that for any interval into V, almost surely the following holds. MC is constant on E if and only if the quadratic variation is constant. You can interchange almost surely and the set of all the intervals because you can take the countable set of intervals and it's enough. Okay? And then for this is a trivial claim. Why? Just note that, okay, another very simple. So first note this is obvious because we have a construction of the quadratic variation as a limit of squares of increments. So if all the increments are zeros, then this increment is 0. It's trivial by construction. From M. And for the other side, just say, okay, some technicality, introduce a martingale and T, which has no, which does nothing until time u, and then starts growing, right? So if u is small, minus mu. If u is small, then minus mt. Minus other way around. If u is small, if t is small, then this is t and this is t. This is 0. And then it starts growing when t exceeds u. And then say, okay, the quadratic variation is, this is an increment of the martingale, so this is difference of two quadratic variations. And let us introduce a stop in time, t epsilon, which is by definition the infimum of all t such that n and t exceeds epsilon. And then say, okay, we know that the expectation of the event that this happens. I mean, let us something trivial. So the indicator. So what I need to prove is that if I know that the quadratic variation is constant on subset of our probability space, then the martingale does not change along this interval on this subset. Okay? So formally, what I should write is that for any okay, let me just try to reproduce it. This expectation, so what is this event? Let's denote somehow event A. Expectation of 1A. And here, what I put is n on the right and nv. Is of course the expectation of n, v, mean, t epsilon. Nothing happens. So what is the role of t epsilon? This is a cutoff to use, to work with true martingales. If I'm on the event A, then t epsilon exceeds v. On this interval, the quadratic variation does not grow, so it starts growing later. So this is that. And this is the expectation. Well, this is obviously less than expectation of just the square of the martingale. Stop there. And this is the expectation of the quadratic variation stopped at this time. And this is less than epsilon. Some abstract nonsense. Some trivial estimates, but again, in words, what is the point? The point is that we know that the expectation of the square of the martingale is the expectation of the quadratic variation. So if we know that on some subset quadratic variation does not grow, it should tell us that the conditional expectation on this subset of n squared is 0. Okay, here is the formal proof. So you see that this guy is less than epsilon, and then you send epsilon to 0. So again, this lemma is there. Well, it has something to do, but it boils down to the identity that the expectation of the squared martingale is the expectation of its quadratic variation. Okay, so this is the theorem. And the last piece for today is the conformal invariance of the two-dimensional Brownian motion, which is of the very much same spirit. So imagine now that we are in 2D, and let we have the two-dimensional Brownian motion. Started from some, say, fixed point. Do I need a notation for this point? Started at some point in a domain. So here is domain U. Here is the starting point. And f is some analytic function. Analytic, okay, in complex sense. And not constant. Constant is too boring. So I do not assume it is one-to-one. Just any analytic function in this domain. Okay? So it maps to somewhere, but maybe not one-to-one. So this is and then let tau u be the exit time from U. And maybe let us assume that it is analytic and continuous up to boundary. Or maybe, okay, maybe we even don't need it. Okay, for simplicity, let it be continuous up to boundary. You can always slightly shrink your domain if needed. I mean, this is not a big price. And this is an exit time. And then what I'm saying is that, okay, if you think about the image of the trajectory, so here you have some trajectory. If you think about its image here, what you see is another trajectory of the Brownian motion. Then there exists a Brownian motion bs, beta s, started at, we note, there in that plane, such that f of bt until the stopping time is distributed in the same way as beta integral 0 t f prime some variable. What should be the variable? It cannot be s, r, r. So this is a very much spirit. What I have here is again a Brownian motion, but with a reparameterized time. And here is the explicit formula for this reparameterization. That's the message of the theorem. Is clear what's going on? And so I just take any domain in the left plane, take any analytic function, think about the image in the right plane, and what I'm saying is that until on the left-hand side it is well defined, I see some trajectory of another Brownian motion in the right-hand plane. Well, probably until some time.
There should be a prime of BR.
It should be squared first, right? And what else? It should be BR, it should be squared. What is of, yeah, thanks. What is of more importance? Yes. Okay, so remark, imagine that you actually have a conformal mapping. Imagine meaning that, okay, it is analytic and one-to-one. Imagine you have some domain here, some domain there, and this is F. Then you can apply this theorem in both directions. And then it tells us, okay, if I'm not interested in the time parameterization, if I just think about the geometric trajectory of the two-dimensional Brownian motion, then the picture I see here, distribution of trajectories, is exactly the picture I see there in terms of distributions of the trajectories. Okay? In particular, all the quantities of a sort like what is the probability that we hit some space in this domain, okay, here and there, up to conformal transform. Okay, good. So, what about the proof? Essentially, this is a computation. I should say that's it. So let us make it, but okay, let f of z be y plus iv. And this is x and y. So the coordinates in both planes. Okay. Note that there's two harmonic functions, right? Because this is an analytic function and it's real part and imaginary are harmonic functions. So because of that, I know that ubt and vbt are local martingales. We saw this example. I mean, this is true in any RD. Okay. Okay. Let us now compute what is d u squared Again, well, it's just a computation by by eta formula. Okay, what I should do? First, there are some diffusion terms. So what are them? This is 2u prime x at the point bt d bt1. bt1 is the first component, plus 2u prime y bt dbt2. This is the second component. And now there are some second derivatives. So what are the second derivatives? Well, this is, I should take another derivative in x of that, right? So what's that? U x plus square. dt, and there is no 1/2 because it's killed in the eta formula, in the eta's formula. Hopefully that's it. Then these two cancel out because the function is harmonic. And what you see is u prime squared, u prime squared. So this is f prime squared. So altogether, this is equal f prime dt squared dt. Everything is computed at this point, bt. Okay. Similarly, if you do exactly the same computation for the second function, you see something dB in some local martingale part plus the same drift. And finally, if you compute the product of two, just an exercise, using Cauchy-Riemann equations. There is no drift term at all.
It's u prime z and u prime. I mean, d u square is equal to not delta plus u prime.
What?
Not f prime.
Not f prime? Here? Nope. So what I mean is that here it's u prime x squared. Here it's u prime y squared. And u prime y squared is v prime x. So what's written is actually u prime x squared plus v prime x squared. So this is f prime squared. Okay? Yeah, well, anyway, this is just a computation. I mean, if the claim is true, which we heard many times, right, then it must work. I mean, there is just no way for this to break down. Okay, good. Now what I'm saying is that, okay, I have now two local martingales. And what I know is that the quadratic variation of the first is given by the integral of that. The quadratic variation of the second is given by the integral of that. And the bracket is 0. And now this is exactly the same situation as we had in the previous theorem. Now make the time change. S is this integral. And conclude exactly as in the previous theorem. So what we will see is that, okay, now there are two martingales, and the quadratic variation of the first is S, quadratic variation of the second is S, and the bracket is 0. Okay, good. Of course, it should be said that there is absolutely no surprise in this result. So, as we know that the harmonic functions, I mean any harmonic function of the two-dimensional Brownian motion is a martingale. So it's a huge amount of information, right? Probably it's enough to reconstruct trajectories. And we know that the class of harmonic functions is stable under conformal maps in 2D. Okay, probably it should be enough to claim that the trajectories of the Brownian motion is also conformally invariant. And maybe the last remark on the blackboard. Just an example. So here it was a conformal mapping, but actually to have something interesting, I mean, it's often useful to consider not one-to-one mappings, but something more general. For instance, the exponent, the exponential. This is an example. If z is exponential of z. So how it works? Here we have the full plane, and here we have the plane without the origin, right? So this is C to the origin. And, well, if this is 2 pi I, so what I'm drawing is that the horizontal lines on the left picture, they're now rays in the right picture, and okay, maybe it's better to use colors like that, okay? And to make it more impressionistic style, okay, if it was here that, it's another color, so on and so forth. Okay, and the vertical lines in the left, they're now circles. Okay? That's how this conformal mapping works. What we now can say from the conformal invariance. So imagine we have Brownian motion in the left. So it's again Brownian motion trajectory on the right. So the claim is that the moving in vertical direction here is exactly corresponds to winding around 0 there, right? So the message is that if you would like to compute some quantities related to the number of full turns, for instance, you make until something happens, then on the left-hand side, this is a much easier question. Because now you see this is just the vertical coordinate. This is one-dimensional Brownian motion. So it's just an idea that, of course, there are many, many conformal transforms. And what the last theorem claims is that there is a huge invariance of the Brownian motion in 3D, which can be used to compute quantities. Right? Stay clear? Okay, good. And let me then conclude by sort of a general remark. So we still have one more lecture. But a general remark of how it fits the whole masterclass program, if you wish. So remember, it was the story about the simplest possible model in discrete, random walks. And then we have two different worlds. The first is lattices, random walks, something like that. The second is continuous limit. And in the continuous limit, what we now constructed is the Brownian motion, and we now have tools to compute things for them. Right? What is the advantage? The advantage in continuum is that there are much more symmetries, many symmetries. And this allows to perform computations. So you cannot do anything of this sort working on lattices, right? So that's exactly similar to, for instance, usual integration. So integrals are about sums, right? So that's about computing sums. But the number of tools, the toolbox in continuum, is much larger because you can perform change of variables, you can do integration by parts. Okay, this is already in discrete, but you know, it's just it's just very useful language. This is exactly the same here. On the other hand, what is also very good to have in mind is that when we speak about some phenomenon in continuum, it might be always very helpful to have a sort of a discrete cartoon. That's what I tried to show you in the first half, when it was a discrete cartoon for the local type, that there is some complicated concept. In continuum, so I just wrote this integral of sine b db. What's that? I mean, is there any sense of this? That in discrete, all issues of such a kind might be simpler to understand. Well, okay, that's more or less the same story happens with the models we are trying to investigate in our research. I mean, so we have some models on lattices or something like that. We have some conjectures for their limits. And we try to make this correspondence working. We try to prove that indeed this converges to that. Try to infer quantities in continuum. What are the natural quantities in continuum from thinking about what are natural quantities in discrete, and the other way around. So that's exactly the picture of interplay between discrete world and continuum one. Okay, that's a sort of a philosophical comment. Sorry for this. And that's it for today.